All right, for this explainer, we're going to need to think a little differently. We're going to be detectives investigating a slow, silent enemy that's all around us all the time. It's a process that costs the world billions, and we're about to crack the case.
You know, you see that reddish-brown stuff on an old bike or a fence, and you just think rust. Seems pretty simple, right? Just what happens when metal gets old. But what if I told you that rust is just the most obvious clue left behind by a much sneakier and more complex villain? You see, rust is really just one alias. The real culprit we're after goes by a bigger name, corrosion, and it has a whole crew of different methods, a whole bunch of ways to take things apart, piece by piece.
So, to really understand this enemy, to get inside its head, we have to learn how to identify it on site. And that's our first case file. You see, the experts classify these attacks based on one simple idea. How easy are they to spot? Think of it like this. Some clues are just lying right out in the open. Others, well, you need to look a little closer, maybe under the surface. And some are so well hidden, you literally need a microscope to find the damage. We're going to start with the obvious ones, the perps you can spot with your own two eyes. Okay, so let's hit the streets. We're on the lookout for the most common suspects, the types of corrosion that don't even bother to hide the evidence. This is our first group of interest in the investigation.
And here they are, our most wanted list. This is our evidence board. We've got uniform and pitting corrosion, we've got crevice, and the really fascinating one, galvanic corrosion. They might seem straightforward, but each one has a totally different MO.
Now, check out the difference in strategy here. On one side, you have uniform corrosion. That's your brute force attack, the classic rust we all picture. It just attacks the entire surface evenly. But then you have pitting. Pitting is more like an assassin. It finds one tiny weak spot and drills down, creating a deep, dangerous hole that can cause a total failure with almost no warning.
And then there's galvanic corrosion. This one's wild. It happens when you put two different kinds of metal together with a little bit of moisture. One metal, the less noble one, basically sacrifices itself to protect the other. It becomes the part that corrodes, and it corrodes fast. It literally creates a tiny, self-destructing battery.
So that battery idea leads to something absolutely critical called the area effect. It's all about size. If you have a small sacrificial piece of metal, like these little steel rivets, connected to a big protected piece, like this copper plate, that small part gets eaten away incredibly fast. But flip that around. Small protected part, big sacrificial part, and the corrosion slows right down. For an engineer, knowing this is a huge deal. Okay, so we've nabbed the easy-to-spot culprits, but some forms of corrosion are masters of disguise. To find them, we have to dig a little deeper. We have to start looking under the surface for hidden clues. And here is our next lineup of suspects. You've got erosion, cavitation, intergranular corrosion. These aren't things you're going to see just by walking past. They are sneaky, internal attacks that require more advanced detective work to even find. Take erosion corrosion, for example. This happens inside things like pipes, where a fluid is constantly moving. First, the movement itself physically wears away the metal's protective surface. Then, the chemical corrosion attacks the fresh, exposed metal underneath. It's this brutal one-two punch. The sandblaster analogy is perfect. It's just happening where no one can see it. And there are others, like intergranular corrosion. Now, this one is really sneaky. It doesn't eat the whole piece of metal. It attacks the glue that holds the tiny metal crystals together. So the surface can look totally fine, but underneath, the material is losing all its strength, basically getting ready to crumble from the inside out. Okay, so we've identified the enemies. We know their methods, we know their tricks. So how do we stop them? This is where our detective work switches from investigation to prevention. And lucky for us, engineers have a whole playbook for fighting back. There are really 5 main strategies in this playbook. First, just pick the right materials from the start. Second, you can try to control the environment itself. The most common fix, of course, is to put up a barrier, like paint. Fourth, you can use a sacrificial metal, like a block of zinc on a ship's hull, that corrodes on purpose to save the steel. And finally, a lot of it just comes down to smarter design. Let's focus on that self-destructing battery, galvanic corrosion. How do you stop that feud? Well, the rules are pretty logical. First, try not to use different metals together. If you have to, put some insulation between them. And definitely avoid that dangerous small anode, big cathode setup we talked about. Oh, and here's a pro tip. If you're going to paint, paint the part you want to protect, the cathode. If you only paint the sacrificial part, you focus all that corrosive energy on any time you scratch in the paint, and you actually make things way, way worse.
So, after all this detective work, why does it matter? I mean, this stuff can feel really technical, but understanding and stopping corrosion is one of the most critical and kind of invisible jobs in the entire world. The stakes couldn't be higher.
And this is why. This quote from our source material is just chilling. A simple rock, just resting against a steel beam on a bridge, can create the perfect hidden spot for corrosion to go wild, creating large holes. We're not just talking about something looking rusty. We're talking about structural failure. We're talking about safety. At the end of the day, knowing your enemy is everything. This kind of specialized knowledge is what keeps our bridges standing, our planes flying, and our buildings safe. Every time an engineer makes a smart choice based on these principles, they're protecting all of us. We've gotten really good at fighting the enemies we know about, but what's next? As we keep pushing science forward, creating new alloys and incredible new materials, we're also creating new battlegrounds. You have to wonder, what new unseen forms of corrosion are waiting out there? And what new detective work is it going to take to find them? It's something to think about.